Matevosyan. I'm a chief engineer at Energy Systems Integration Group. I want to welcome you to our 2023 ESIG monthly webinar series and give you a little bit of background on ESIG. For those of you who are not familiar with ESIG, we are a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of the energy transition. We do this through workshops, tutorials, webinars, blogs, working groups, and task force activities, and producing technical resource materials. ESIG also serves in a leadership role on the Global Power System Transformation Consortium, or GPST, whose mission is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scope and speed. ESIG leads Pillar 1 of the 5 pillars, which deals with research agenda of the system operators. For more information on GPST, please go to www.globalpst.org. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on ESIG website. If you are new to ESIG and you like what you are hearing, we strongly encourage that you follow up with us, and I think you'll be pleasantly surprised. ESIG membership will give you an opportunity to participate actively in all of our working groups and task forces, and you can find us on the web at www.esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. Okay, a few logistic matters before we get started. First of all, the phones will be muted for the duration of the webinar to avoid any unnecessary distraction. For the Q&A, please go ahead and use Slido platform. So to ask your question, please go to slido.com and enter ESIG19 as an event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions, and this allows you to cast your vote and help us prioritize the questions that we ask. We plan to save 10-15 minutes of time for Q&A at the end, and then we'll wrap up at the top of the hour. An email with link will be provided once the video file has been posted. We also plan to provide short responses to all unanswered Q&A questions. So please don't be afraid to ask your question and vote them up on Slido. Okay, so today's topic will be stability enhancement of utility-scale renewable energy plants in weak grids to enable widespread development of renewable energy resources, particularly in weak parts of the network. The Australian Renewable Energy Agency funded a 2-year research project at Monash University in 2020. This webinar provides an overview of the project's finding and developed solutions with specific focus on grid following and grid forming inverter control strategies and synchronous condensers. The solution aims to address the challenges of integrating inverter-based resources into power system and enable a smoother transition towards cleaner energy future for Australia. So I would like to welcome our today's presenter, Dr. Behrooz Bahrani. He received his PhD from EPFL in Lausanne, Switzerland, in electrical power engineering in 2012. From 2012 to 2015, he was a postdoctoral fellow at several institutions, including EPFL, Purdue University, Georgia Institute of Technology, and Technical University of Munich. Since 2015, he has been with Monash University in Australia, where currently he's a senior lecturer and the director of a Grid Innovation Hub. His research interests include control of power electronic systems, applications of power electronics in power systems, and grid integration of renewable energy resources. Following Charlie's tradition, I went on LinkedIn and checked, and I'm happy to report that Behrooz and I, we have 236 common connections, which means we worked with many of the same people over the years. I consider it's an honor that Behrooz is here with us today to present on his research. Just a short reminder, again, use Slido at slido.com with the event code ESIG19 to ask your questions and vote the questions that you like up so we can ask them during the webinar. Okay, without any further ado, let us go ahead and get started. Behrooz, over to you.
Thank you so much, Julia, for the kind introduction. And hello, everybody. Good morning, good afternoon. So I've let me first share my screen. I'm hoping that everyone can see the screen, and I'm now full screen. Is it
Yes, we can see it.
fantastic? Thank you so much. So, as Julia introduced, today I'm going to talk about the findings of a project funded at Monash University in 2020 by the Australian Renewable Energy Agency, or ARENA, to look into different challenges and problems around grid integration of renewables into the power system, particularly in weak areas of the network. Well, I will start with a brief introduction, and then I have categorized the presentation into multiple sections, particularly grid following, grid forming inverters, and then a new breed of inverters that we looked into in the project, and finally synchronous condensers. And then I'll conclude the presentation, hopefully in 45 minutes. So to begin with and give you an understanding why this project and why it was actually important for us and funded. Unlike many other countries, Australia has a very, I would say, different network. We've got a network which is very long, and then it's not a mesh network, meaning that we've got lots of issues with system strength in our network. When you look at this figure to the right, this shows you these dots actually represent system strength in different parts of the network. And system strength typically determines how reliably and securely you can connect your inverters to the grid, and how securely and reliably your system will operate up on various contingency. And this is the situation almost now-ish. So this figure was taken in 2019 from AEMO's website. And when you look at it in 2028 to 2029, it is projected that we'll be having more of these red and orange lines in our network. And if we keep doing what we're doing, this would be the situation in 20 years from now. A lot of red lines, red dots in the network, which makes it very, very difficult for us to integrate more renewables. And the main problem for us in Australia is that quite a lot of these red dots are actually at places where we've got very, very good potential for renewable energy. So yes, we've got some good green dots, but they're not where the most potential for renewable energy is. So if we want to integrate more renewables, either we need to reinforce our grid, or we need to come up with solutions that we can use in these weak areas to be able to integrate more renewables. When we were going to start the project back in 2019 was the time that we were writing the proposal. We were looking into the literature, and this very good CGRE working group report on integration of renewable energy, wind into weak networks, were actually telling us that there are a number of problems when you're integrating renewables into weak grids, particularly control interactions and instability, failure to ride through disturbances, electromechanical oscillatory stability, islanding issues, subsynchronous oscillation, all sorts of problems that were there. So what we did, we defined this project with a number of aims, mainly around understanding why systems become unstable in weak grids and coming up with solutions, particularly around grid forming and grid following inverter control, to be able to integrate more renewables into the grid. So the project outcomes were supposed to be increased penetration of solar and wind farms, maximize generation capacity for existing wind farms, and obviously increase reliability and security. So the project was a 2.5-year project. Started right in the middle of COVID, which was like a very, very big challenge for us. Recruiting people and starting a project was not trivial. So ARENA funded roughly around 559K to the project, and we started a project with a number of partners, and we defined 3 different tasks. The first one was around grid classification and testbed development. The second one was around grid strengthening solutions, coming up with solutions for syncons and grid forming inverters, their control and allocation, and finally internal control and interaction of farms. And well, we had a number of partners, AusNet Services, AEMO, and ABB, and then Hitachi ABB, and finally Hitachi was actually also part of our project, and ARENA was the main funder. So, like I said, we defined four main categories for ourselves. Well, the third category actually came up during the project, but three categories to begin with. Grid following inverters, grid forming inverters, and then a new family that we call it power synchronous grid following inverters, and finally synchronous. And we thought that, okay, we'll look into these areas in order to come up with the solution that we want. Particularly grid following is important because obviously the largest fleet. Grid forming obviously important because it's an upcoming and it is becoming actually now established variation of control, and power synchronized, which would be well, I'll talk about that later in the presentation. Obviously, synchronous is a traditional solution, and we wanted to see how we can use them better in the network. So after this very brief introduction into the project overall, let's talk about different aspects of the project that we'll look into. Well, with grid following inverters being the most common approach of integrating renewables into the grid, we started with grid following inverters. Obviously, it's a relatively well-known, well, very well-known structure of integrating renewables into the grid, controlling converters in the grid. Pretty simple structure, pretty well-known performance and good performance in actually strong grids, and typically pretty much stable under various disturbances. However, as soon as you go to weak grids, challenges begin. Small signal instability due to PLL is pretty well known, and it of course requires an external grid because it needs to synchronize itself with an external grid. And as soon as you've got low system strengths in the network, like what we have got in many places in Australia, we'll have failed synchronization. So one of the major things for us was to understand better exactly how this grid following inverter will become unstable. So what we did, we actually looked into, well, we wanted to go beyond normal solutions in the literature, and we went into the area of nonlinear control and understand how this system might become unstable and under what exact scenarios the PLL can become unstable. So what we did to begin with in the beginning of the project, we looked into grid following inverters and took these nonlinear approaches to do two things. One, to assess PLL-based or PLL-equipped grid following inverters and understand under what exact scenarios they will become unstable. And when I say exact scenario, we wanted to take into account the PLL structure, the PI controller in the PLL, and also the impedance of the grid. So combining all of them and understand exactly under which scenario this system will become unstable and coming up with some sort of an index. And then secondly, we wanted to use nonlinear approaches to expand PLL capabilities and come up with a solution which is stable for a wide range of scenarios. So what we did with using, and we derived a system model, both PLL and the grid, and took a nonlinear approach based on the Apanov theorem. We came up with a domain of attraction. So we found the equilibrium point of the system. If this is the system, these equilibrium points, we found them that, okay, which ones are stable and which ones are not stable. And based on that, we came up with the domain of attraction for the stable points. And we actually proposed a new system strength index, which, like I said, takes into account not only the grid impedance, but also the internal controller of the grid following inverter. Additionally, using the same like models that we developed, we also use feedback linearization, another nonlinear technique, and we expanded the PLL capability and its domain of attraction. So this is the new PLL that we designed. So it has an added structure here based on feedback linearization, and we proved that we can expand the domain of attraction of this system to the whole plane, so it becomes a very, very capable PLL. And the details for these two, the system strength index and also this new PLL, are in the two references here. Both of them are published and available. And in the presentation, I will refer to a number of publications that we worked on, and I'll try to talk very, very briefly about each concept. And if you're interested in any of them, please feel free to go and look into these references. So the first one here talks about that system strength index, which takes into account the controller and the grid. And the second one is the new PLL that expands the domain of attraction of a PLL to the whole plane, which makes your system stable under various scenarios. The second aspect of grid following inverters that we wanted to look at in the project was output capability curve. And we wanted to understand, similar to a synchronous generator that you've got this output capability curve, we wanted to understand how we can come up with an output capability curve for grid following inverters, taking into account different limits. So in the synchronous generator, we've got turbine limit, core and heat limit, field current limit, all sorts of limits, and you would have this green area as your capability. So we wanted to do the same thing. We wanted to look at converters and understand the thermal limit, stability limit with PLL, energy resource limit, voltage limits, and static limits, combining all of them and coming up with an output capability curve. So this is when you only consider, this is the output capability curve when you only consider the thermal limit, but as soon as you add other limits that we looked into in this publication here, which is unfortunately still under review, in this, I guess, third round of review in IBR transactional power systems, hopefully will be published very, very soon. But we looked into all sorts of limits that a converter can have. And we came up with this capability curve. So this is a typical case. Now, if you, for example, connect it to a weaker grid, you'll see that this line will actually limit you as well. So you wouldn't be able to operate here, for example. Now, if your PLL is not very well tuned, again, the PLL will pose another limit for you, and you will come up with this particular capability curve. So we have defined all of these limits, and we actually came up with this capability curve. So we'll tell you where you can and cannot operate. Now, you know, what is good about it, the thing that is good about understanding your limit, obviously, is you know that where you can operate and you cannot operate, but also you might be able to come up with interesting solutions to expand to expand your maximum transferable power, to expand your output capability curve. Obviously, one of the some of them you can't change. These, if I go back, limit 1 to 3, you can't change these things, but these two you can change them. You can change them by changing actually the PLL and adding certain structures to the controller. So if you tune your PLL, you can get rid of the PLL problem, but also if you have certain types of controller for your reactive power, and when you know exactly how you're limited, you would be able to expand the capability curve. So what we did, we actually added that again. All of the details are in this paper. Hopefully, it will be available online very soon. But it can easily expand the maximum transferable power for you. So this simple case study, an experimental case, this is without that controller, without that external controller for Q, and this one is with the external controller with the aim of expanding the maximum power, the transferable power. And as you can see, we can inject more and more real power. The blue one is the real power. So and then this one is actually the injected reactive power. By changing slightly the reactive power, you can actually get a lot more out of your converter. So after looking into these aspects around grid following inverter, understanding where and when they will become unstable, and having a new PLL, we thought, okay, now it's the time to look into alternatives. And obviously, grid forming inverters, a very obvious alternative to grid following inverters. We looked into grid forming inverters for a significant portion of the project, and we looked into different aspects of it, particularly control. But well, what is grid forming and why grid forming? So we know that with all the new inverter-based systems coming to the power system, we've got lots of problems in terms of inertia, system strength, fault current, and control interaction and oscillations. And we would like to replace the grid following inverter with a grid forming inverter, which is essentially, you can look at it as a voltage source. So essentially, instead of having a current source, it is a voltage source which gets synchronized with the grid using power synchronization. So, well, I think it's no secret anymore that grid forming inverters have very, very good performance in weak grids compared to grid following inverters. They can provide system strength and inertia. And they can also operate in standalone mode, meaning that they don't need a separate external grid to connect to. They can actually form a grid for themselves. A very quick recap, if you're not very familiar with grid forming inverters, the way they operate is that you've got this VSC. When you're connecting it to the grid, there will be, of course, like a grid following inverter, there will be a filter there. You will have an internal current controller which controls the current. The references for this current controller for you, it's a typical current controller. The references for that are given to you by a capacitor voltage controller. It controls the voltage at the point of connection and gives the reference for the internal current controller. The references for your capacitor voltage controller, or PCC or POC voltage control, is given to you by a primary controller. And the primary controller is responsible for creating the frequency with which everything is actually, all of your DQ transformation are actually using that frequency there. And what's inside the primary controller determines the performance of the overall system typically. And you can have droop control with filters, or you can have VSG, which is one of the most common approaches that is used in industry at the moment. And we were actually essentially working on this primary loop to understand how we can improve this primary loop and how we can get more out of this primary loop and add to the performance. And obviously there's a power calculator here, which gives you the actual power, and then you compare with the references and create the signals that you would like. This is a very typical controller for the primary loop for the real power. So for the reactive power, either you can use a similar virtual synchronous generator type control, or you can just use a droop control, which is probably the more common way. Now, this is the emulation of the well-known swing equation. And you've got a damper, you've got a J, your inertia. So this is, like I said, very, very well known. The performance is very well known, and it is used in many implementation of VSGs around the world. But there are a number of problems with that. One of the things is that the performance of this structure is very much dependent on the XR ratio and SCR at the point of connection. So if you change the SCR and XR ratio, well, you get different dynamics there. So this is a very simple case where we have changed the SCR and we've kept the XR ratio constant, but changing the SCR from a pretty strong grid to a pretty weak grid, you can see that oscillations will emerge, particularly when you're in a stronger grid. You've got more of these oscillations. So yes, of course, it can work. It won't become unstable, but it's not a very, very great performance. So one of the things that we wanted to look into in the beginning, we wanted to see, okay, first of all, what is the exact relationship here? How is the relationship between XR ratio and impedance of the grid and the performance of the VSG? We wanted to see how in strong grids these poor dynamics is actually coming along. So we wanted to understand that, okay, how we can get rid of these oscillations and how we can change the settling time and overshoot. So we saw that, okay, we might be able to control this VSG such that all of these settling time, overshoot, and damping might be fixed if we determine D and J, those two parameters that we've got in VSG. If we can tune them properly, maybe we can actually get good performance at all grid strength scenarios. So, and one other challenge for us was to exactly keep the control structure. We didn't want, in the beginning, we thought, okay, we'll keep the VSG structure, but we want to control that D and J in a way, or tune D and J in a way that we get the best possible performance. So to do so, we came up with this adaptive control structure. All the details for this adaptive control structure are in this publication here. It's already available. So in a nutshell, what we did, we adaptively tuned D and J to values which are actually giving you the best possible performance for any grid strengths and any grid impedance. How we did that, we actually started with the power flow equation, we linearized them, and then we defined the desired performance, and we came up with some equations, again, all the details in this paper, I very much recommend reading it. It gives you a very good understanding of the relationship between all those dynamics and D and J and the impedance of the grid. And based on that, we came up with an adaptive way of tuning D, J, and some other parameters in the controller based on the impedance of the grid. Now, if you know exactly the impedance of your grid and you know that it's not going to change, fantastic. You can just measure it once and then use all the equations that we have developed in this paper and tune your D and J. But if you don't know it, or it is subject to change, we have actually come up with this adaptive way of estimating your grid impedance at any point in time using a signal injection, because, well, the grid impedance might change. It might change over time. So every time that we wanted to, for example, apply a step change or something, before applying the step change, we adaptively tuned the system based on an injection of a signal, 75 hertz signal to the grid, and estimating the grid impedance at that point. So this is the performance. This is without any tuning. This is just a normal VSG, and this is with the proposed tuning. So we, if I think this is easier to see here, the green one is without any tuning. The red one is with the tuning, and you can see that there is a slight, injection of a signal here to measure the grid impedance. And then by measuring that grid impedance, you can actually tune your D and J very, very properly to have this very nice and damped response instead of these oscillations. Obviously, you don't have to inject this signal all the time. If you know that your grid is almost fixed, it's not going to change much, you don't need to do it. Or you might want to do it like every now and then, I don't know, every day, every month, every week. You want to just send a signal and test your grid, and based on that, adaptively tune. Or you just might decide that, oh no, my grid is not changing at all, so I just tune it once, I send the signal once, and then I tune D and J. But regardless, if I go back here, this paper gives you very good guidelines on how to design D and J for a VSG. Even if you don't want to adaptively tune it, you can tune it once and just leave it there. This one tells you, shows you how important it is in stronger grid. This one, it was a relatively weak grid, but in stronger grid, if you don't tune your D and J, these oscillations can be even worse. So after doing this, okay, fine, good. We can tune D and J. It can be actually a good performance. But what if we actually change the performance? The structure of the VSG. So previously we didn't have these two parts, and it was only an integrator here. But we thought, okay, let's actually add certain things to the structure of the VSG and see what we can do. So we added a pole and a zero to this structure. And we came up with this method that we call the generalized virtual synchronous generator. Essentially, if A and B are the same, so it is exactly identical to the VSG. But if A and B are not the same, you've got a different controller which can still act like a VSG, but it can give you even better performance. And it can actually, those problems that it would have in weak grids would go away, and you don't need to adaptively tune anything. It can give you good performance regardless. But when we looked a little bit more carefully, we saw that it is still a little bit of overshoot in this. So we actually made some other tweaks there and changed this structure a little bit more. All of the details are in this paper, Generalized Virtual Synchronous Generator Control Design. We tweaked it a little bit more. We added a zero in actually the closed loop, and this is a damping correction loop. And it actually helped us to get even better performance in weaker grids. Just to show you how these three, the normal VSG, generalized VSG, and CG VSG operate, you can look at these experimental results. This is a stronger grid. So this one is a normal VSG. This one is a GVSG, and this one, the last one, CG VSG, compensated one. You can see this has very nice and damp performance without any particular tuning. Any adaptive tuning, and this one is in a weaker grid. So in a weaker grid, the problem is less pronounced. Like I said, typically the stronger the grid becomes, the more oscillations you see in the system. So as you can see, the impact of grid strength on CGVSG is not much. Regardless of grid strength, it performs pretty well. Now, We actually went one step further and thought that, okay, sometimes it is a little bit difficult to probably use the CGVSG because we are relying on simplified parametric models. We were not looking into the very exact model of the system. So we thought that if we wanted to tune the system very, very accurately for a particular case, what can we do? So we looked into frequency domain control designs, and we use H-infinity based control design. It's actually a little bit too advanced here. I'm not going to go through all the details, but using an H-infinity control design, we managed to design another active power controller for VSGs, which gives you exact performance you need. It actually takes into account all of the dynamics of the system. And this is just a small comparison between Droop VSG and H-infinity. The red one is the H-infinity, and it gives you the fantastic performance that you need. It complies with all requirements very, very well. But I acknowledge that this is a little bit difficult to tune, and it's a little bit difficult to actually design. If I go back again, all of the details of this controller is given in this publication here. But again, I acknowledge that this can be a little bit more challenging and difficult to tune initially because of all the control design procedure involved. Now, after designing all of these controllers, I said, okay, what else? What else can we do? We looked into the controller and we realized that, okay, typically we control VSGs, assuming that the power loop, real power loop and reactive power loop are decoupled. But this is not always the case. Typically, when you've got a system in which the XR ratio is not very, very high, meaning that it's not fully inductive, you will have coupling between real and reactive power. The typical way of solving that challenge is by adding virtual impedance or inductance in the system to actually make your system inductive. But we thought, okay, why do we do that? Why don't we design a 2x2 controller for the VSG, so both for real and reactive power? So we took a multivariable approach and we designed a multivariable controller for the VSG such that it controls P and Q simultaneously in a 2x2 controller that we designed. And this is the controller, which is very similar to, well, this is in Z domain. It is very similar to a PI controller or P controller. You can actually determine which controller you want to have. And we took this loop shaping based method. We're based on, again, frequency domain response of the system. And we designed a controller which is very similar in terms of performance, in terms of Rokov performance or any other matrix that you've got. It's very similar to VSG, but it gives you this very nice decoupled control. So if you look at the VSG, normal VSG in blue, VID, this stands for virtual impedance. And OMPC is the controller that we designed. So when you look at the red line, this is P, this is Q. So when you change P, almost no change in your Q, while in the other two, there is actually a change in your Q because they're coupled. But with the controller that we designed, we can fully decouple P and Q. And it's just in terms of other requirements, it is identical or even better than the existing methods, but it can fully decouple your P and Q and you'll have a much better control. We tested it for different scenarios. In every scenario, it actually works very, very well, no problems at all, and it can actually work like it can ride through disturbances, ride through frequency disturbance, voltage disturbance, similar to a normal system, a normal VSG. But still, when you're changing your P and Q, you've got this very nice decoupled controller. Now, after designing all of these controllers, we looked a little bit into transient stability of grid-forming inverters, and we wanted to see how the system will operate when we are actually experiencing a fault. We, of course, started with a normal VSG, and this is still work in progress for us. We are currently working with GPST to further advance this study. This was just the very beginning of that we did in the ARENA project, and now we are continuing that transient stability because it's a very big topic at the moment. But to begin with, we looked into the performance of a grid-forming inverter upon fault recovery, and we saw that when we have a fault in the system, particularly when we've got weaker grids. After recovering from the fault, we can have lots of oscillations in the network. We can have lots of oscillations in the performance in the for example, real power here. And we thought, okay, what can we do? Typically, if you don't have a very nice tuned controller, and if you've got a deep fault, you can actually experience all of these things. And one way of doing this one way of actually solving this problem is to add virtual resistance to the controller. So we started by looking into the problem. We added fixed virtual resistance to the problem, to the controller, and it could solve the problem to some extent, but it's not the best way. So we decided to actually come up with an adaptive virtual resistance to better damp the post-fault oscillations. And we came up with a nice, very interesting and elegant approach. It is published in this paper here. The idea is that instead of actually relying on a fixed resistance, or instead of actually just keep the resistance always constant, we came up with this approach that would adaptively change the amount of virtual resistance in the system depending on different signals that it receives from the network, to come up with a better and nicely damped approach. So this is the amount of the RV, or virtual resistance, that we put. So this is when the fault finishes. As soon as the fault finishes, we come up with a methodology to adaptively change the virtual resistance to come up with a better damped response. So what we did, actually, we took this state machine. Of course, I'm not going to explain it exactly. All of the details are in that paper. But the way it works is that it looks at the power, and based on the power, and based on this state machine, it decides how much virtual resistance at any point in time after fault recovery is required to come up with a better response. So to see how it works, this is without any virtual resistance. So we've got all these oscillations. This is when you put a fixed virtual resistance in the system, particularly when the system is actually strong. It actually makes the system unstable. So not only it's not helping, but it's actually making the system unstable. But with our approach, almost for all grid scenarios, you can have a very nicely damped response upon the recovery, and you can very easily recover to a very nice state without excessive problems. And when you look at this, is the virtual resistance for different scenarios that state machine is giving us, and we're putting into the controller. Again, all of the details you can find in that paper. A pretty nice way of getting rid of all of those challenges and problems of fault recovery. Well, the topic of grid forming inverter obviously is a big topic. It's attracting a lot of attention these days, and that is not the end of our studies. We are still working pretty much on this topic on a daily basis. We are coming up with different approaches for grid forming inverters, but this is what we did in this ARENA project. Like I said, we're these days focused on transient stability of grid forming inverters. A number of publications we've just published, and you probably can find them online. And we'll be, of course, continuing that study. But well, today is about this ARENA project. And that was all of the topics that we studied during our ARENA project on grid forming inverters. Now, it's time to go to our third family of inverters that we studied in this project, and that we call power synchronized grid following inverters. It is essentially some sort of a combination of a grid following inverter and a grid forming inverter in order to solve the challenges that we've got for grid following inverters, while keeping the controller still grid following, meaning that still we can follow the grid and inject the maximum power that we can to the grid without needing to have any grid forming control, while not having the issues of synchronization in weak grids. So the way this works, this strategy works, is that still, again, the idea still is to inject the real and reactive power to the grid without needing to form any voltage at the point of connection, without needing to form the voltage, controlling the voltage, but eliminating the need for a PLL. It was first published in 2021, power synchronized grid following inverters without a PLL. And then we've been working on it and actually completing or adding features to this controller. But in a nutshell, the idea of this controller is that it will measure the power, and then it will compare it with its reference, and it will give it to a 2x2 controller, which can be designed in a number of ways. And this 2x2 controller will give you the reference for an internal current controller, and also will give you the frequency. Now, it is essentially, when you look at it, essentially eliminates the need for a voltage control. And instead of being actually, because if you remember, if you know the exact structure of a grid forming inverter, it forces the Q component of the voltage to zero in order to have real power being proportional to your ID and reactive power proportional to IQ. But in this approach, we're forcing IQ reference of current to zero. And with ID, we can control both P and Q while we change omega as well. So by changing omega and ID, we can control P and Q. And again, this inner current controller is identical to any other current controller. The only difference here is that we do not have that voltage loop, we do not have that PLL, and this 2x2 block will give you the frequency, essentially will synchronize itself with the grid, and you will get you'll be getting the reference for your D current as well. And it can control without having any PLL, and it can actually perform very, very well in both the strong and weak grids, and you have absolutely no issues there. But with the very first configuration or variation of this controller, we had a number of issues. Well, the first issue was that we were tuning these controllers here with an optimization approach. It was a little bit difficult to do that. The controller bandwidth was dependent on the operating point, and we had some oscillations when we had unbalanced grid. So but the results were pretty good in weak grid, in strong grid. If we didn't have all those, if we exclude the difficult control design, and if we exclude the fact that it was the dynamics were dependent on the operating point a little bit. So apart from that, everything was very good, and we could operate very well in both types of grids. But we said, okay, why not?
Can you try to wrap up within the next maybe 8
Sure.
minutes to leave some time for questions? Thank you.
Absolutely. Yeah. So we thought, okay, what we can do, we can come up with some sort of adaptive tuning. So we came up with this linear parameter varying control. So this is a variation of this controller. So adaptively, we are tuning the parameters here without having any optimization approach. So we know exactly, we came up with the equations that would give us the performance that we need. And we can adaptively tune the controller based on the operating point. So it would give us it would give us constant constant rise time or unchanged dynamics when we change the operating point. And everything was working well, except the fact that we realized, hey, now when we have large deviations in frequency, we've got some oscillations. Still, unbalanced grid was a challenge. So we went to another type. We use a second order controller here, again, based on the equation of the system, no optimization-based tuning or anything. And we managed to actually control this inverter exactly with those fixed dynamics, stable in many different in all operating points, strong and weak grids, and everything was very good. The only challenge was still unbalanced grid. So in unbalanced grids, we had some issues when we had negative sequence in the system, but we have also one solution for that. So this is one of the experimental validation for this. So in very strong grid, the system works pretty well. In weak grid, the system works pretty well. So no problems, no challenges here. And for the unbalanced grid, we added a negative sequence, current controller, in order to get rid of any imbalance in the system, and we simply added that in parallel to the controller that we designed. This one is still under review. We're hoping that this will be available online very soon. But this configuration, version 4 of the very original idea And it works actually pretty well. We're hoping that we're already talking to some of the OEMs to see whether this is of interest, and maybe one day it can actually be a controller that you can see in grid following inverters, because it will eliminate the need for PLL and can actually give you some very interesting results in weak parts of the network. So this brings me to the last section that I want to very briefly talk about. So synchronous condensers. I think it's not, of course, a new technology. It's been around for years and years. Well, you probably know synchronous condensers pretty well. Now they're synchronous machines without a prime mover. Essentially, what they are, if you're not generating power with a synchronous generator, you've got a sync-on. So they can contribute to short circuit power. They can actually give you voltage support through their exciter. If you add flywheel, they can give you inertia as well. But the problem with them is that installation operational cost and also lead time. So it takes quite a long time before you can have a sync-on in your system. So we thought, okay, with all these challenges, let's come up with some planning or allocation and sizing strategies for sync-ons. And in the project, we came up with 2 approaches, and most of them are published and available. One of them is based on a meta-heuristic algorithm, such as genetic algorithms, in order to come up with a planning or allocation strategy for sync-ons. And then the other one is based on convex optimization to give you a global optimum point when you're going to install synchronous in your grid. This is a very simple algorithm. So the idea was to look into SCRs, and also the cost function which was developed is based on operational cost and voltage deviation in the network. And then based on that, we came up with these 2 approaches to tell you where exactly in your system you need to put these sync-ons in order to get the best out of your investment. Again, all the details of these 2 allocation strategies are in these 2 publications here. Just to show you how well it works, this is a fault right-through test without any sync-ons in the system, and then we put the optimal sync-on at certain points, and it can get rid of all the challenges that you've got with minimal amount. But this one was the generic, the meta-heuristic approach, meaning that it is an optimal, but it is not a global optimum point for you. And we also looked into this convex optimization base, and we found a very, very nice and accurate allocation with the minimal amount of capacity of sync-ons in your system, and it can get rid of all of these oscillations for you with the minimal capacity of sync-ons in your system. After doing that, we thought, okay, what else can we get out of these sync-ons? We thought, okay, maybe we can look into the exciter of the sync-ons and come up with better exciters. Exciters obviously are pretty standard, and you've got a number of different exciters, and we pick the most common one and say, okay, how can we make it better? So we looked into this particular exciter, and we came up with a better controller, a robust controller based on the system model. So we actually identified the system model at the point of connection, considering different SCRs and XR ratios. And we actually designed this sync-on exciter, which will give us better performance when we've got different disturbances in the system. Again, the details of this exciter controller can be found in this publication here. And this is just some basic results. The blue one is a normal AC1A exciter, and then the red one is what we designed. So up on fault, when we've got a deep fault in the system, AC1A in certain areas might become unstable, and not only won't help you, it will make your system unstable, but with the controller that we designed, it can stay stable even in very, very nasty faults, and it can give you very good performance and support your grid without any issues. So I think that summarizes all of the points that I wanted to talk about. Just a very brief recap. For grid following inverters, in the project, we actually had an index to determine the stability and I think I lost my headphone. Do you still hear me?
Yeah, sound went out for a second, but now we can hear you again.
If you just give me 1 sec. Okay, can you hear me now?
Yeah.
Okay, fantastic. I guess my headphone just died, so I go to my speaker. We had a modified PLL as well, which actually we expanded the stability margin to the whole plane, very, very large domain of attraction. A new breed of grid-following inverters we actually introduced, and a number of control strategies for grid-forming inverters, and also output capability curves for grid-forming and grid-following inverters. And finally, on syncons, we looked into 2 allocation techniques and an exciter control. So this is a very, very, I would say, high-level overview of what we did in the project. And well, this project is not, like I said, the project itself is done, but we are still working on these topics. Like I said, transient stability of grid forming is a big topic for us these days. We're expanding our activities to grid forming in control of wind, type 3, type 4 winds, and also frequency domain stability analysis, which is a topic of a newly funded ARENA project for us. Hopefully we'll hear from that in 2-3 years time from me. But before I finish, just some acknowledgement of my team. Well, all of these things that you saw is the work of like a team of brilliant researchers that I worked with in the past couple of years. I've been working with a number of research fellows and a number of PhD students in my team. Big thank go to all of these team members. They did a brilliant job in actually coming up with all these concepts that you saw. Some of them are already gone and started jobs elsewhere. Some of them are still with us. And we are looking forward to more contributions from our team members. Well, thank you so much. And I think I'm hoping that I didn't go over time.
Yeah, you're good. Thank you so much. It was a very interesting presentation, tons of questions here. So we'll get to as many as we can now, and then maybe you can shortly answer offline what remains. One kind of general question, how system inertia being addressed as rotating generation is replaced with inverter-based resources?
Well, I think the problem of inertia, well, obviously it's a big problem. And when you probably when we were talking about grid forming inverters, you saw that in that in the structure you've got a VSG, and that VSG you've got a J, like an inertia, a synthetic inertia that you can actually provide with your grid forming inverter. So the hope is that the synchronous inertia that is retiring will be replaced by this synthetic inertia that the grid forming inverters are providing to the grid. And also the other approach towards the end of the presentation, I was talking about syncons, and obviously syncons are a very good source of providing inertia as well. They're essentially your they're essentially your synchronous generator. But in addition, I mean, well, the only thing is that they don't provide energy for you, so they can still give you that inertia if you like. So my thinking is that a combination of the synchronous inertia from syncons and the synthetic inertia from grid forming inverter will be the future. Currently in Australia, for example, we've got a number of syncons operating and a number of syncons planned to be installed. And then we've got a good number of grid forming inverters, well, a few which are already operational, and a very good number of them which are coming. So I think the combination of these grid forming inverters and syncons will compensate for the lack of synchronous inertia in our grids. And this is probably the way to go. Well, for how long we'll be relying on synchronous condensers, I don't know. The thing is that synchronous condensers, when you put them into the grid, they will be operational for 20, 30, 40 years, like a synchronous generator. So I think for a long while, we'll be having a combination of syncons and inverters in the grid, but maybe at some point in 30, 40 years from now, we will completely replace all of these synchronous condensers with IBRs as well, which is a possibility, but I think it's just a matter of time.
All right, thank you. Then the next question is the short circuit ratio based metric is used to estimate inverter-based hosting capacity, considering system strengths constraints? And I understand you propose a different metric, so maybe I'll also combine with another question. That metric that you have presented, I understand is not based on short circuit ratio, and can it be easily implemented in the control room?
Yes, so I think we are referring to this particular work here when we were actually having a system strength index. So that system strength index, it does incorporate the grid impedance, right? It is a part of that system strength index is the grid impedance, and essentially grid impedance is your short circuit ratio, kind of. But also it does incorporate the controller parameters of your inverter, particularly the PLL. So it is probably not easy for like an operator to use it, because an operator wouldn't have access to the PLL parameters. But if they do, then they can. But the problem is that most of the time IBRs come in a black box, so you don't know exactly what you've got. But if OEMs are willing to maybe share that piece of information, then it can be incorporated into these system strengths. And the good thing about it is that unlike SCR is a metric, but a very limited one. It actually won't give you exactly whether the system is stable or not. It will tell you that maybe you're actually going to a region that you might have issues, but I don't know, maybe be careful. But if you have all the controller parameters as well, particularly in this case, the PI for the PLL, you can exactly predict whether you are stable or not. And if you're not stable, you're not stable. But if you're stable, it will also tell you how far from stability you are. So it's a pretty good metric if you know the grid impedance and if you know the parameter of the PLL.
Thank you. Sounds good. Next question is there a reasonable explanation why VSG performs worse in a strong grid?
Well, actually, let me go to that. Okay, so this actually this is where we were talking about the adaptive VSG. So if well, I very much encourage you to have a look at this paper. This actually tells you exactly what happens when you've got a VSG connected to a grid with an impedance, which is always the case, of course, and it will tell you exactly how the dynamics of the VSG will change if you change the XR ratio and R and L of your grid. So we have actually derived all of the equations there, and it tells you the very exact relationship between the grid impedance and grid strength and the performance of your VSG when you've got a fixed D and J. So I think best is just to refer you to this paper and look at, because all the equations are there and exactly tells you what happens to the performance. And you will see that when you've got a stronger grid, if you're not careful, it will impact the dynamic performance like a lot. So you have to be extremely careful when you're connecting to a stronger grid. And what we did here, you see that this is still this one. This is still a strong grid. So the red one is a strong grid. The green one is also a strong grid, but the green one hasn't been tuned exactly to the for that particular condition, but the red one is exactly tuned based on the equation that we've derived. So we shouldn't say that by default in a strong grid you will have bad performance. No, in a strong grid, you can also get very nice and damped response, very well-tuned response. But if you're not careful about the tuning, you can also get very nasty response as well. So the idea is to be able to tune it. The idea is to make sure that you know your grid and tune for that grid in order not to have these oscillations, these green oscillations there.
Thank you. The next question is, are any existing inverter-based resources, OEMs, utilizing a similar type of control that you have tested, or do you have any recommendations for them to test and put it into practice?
Well, typically these things I think take some time to go from research and academia to a product. But we did have one of the OEMs with us in the project, Hitachi ABB, well now Hitachi Energy. They were with us in the project, and they were like they know exactly what we have been doing. So I'm hoping that at some point they will pick up some of these. But I don't know of any particular OEM at the moment using any of these. All of these are now in the public domain. All of them are published, and this is obviously our hope that some OEMs at some point will use these. We are open to talk to any OEMs who is keen to use any of these. We are keen to work with them to help them to better understand and test some of these in their actually products. But I don't know of any particular OEM who is using any of these at the moment. But like I said, if there are OEMs interested, we're more than happy to work with them and to actually help them to incorporate some of these in their products.
Thank you, Behrooz. I wanted to ask, do you have another 10 minutes? Maybe we'll hit a bit more questions.
Yeah, I'm available, so we can probably.
So we'll go on for another 10 minutes. Just there are a lot of good questions I would like to ask online rather than you responding offline. There was a related question that I wanted to ask. That power synchronized grid following inverter technology that you have presented, can it be implemented in already existing grid following inverters that are online? Basically, can you retrofit grid following inverter with this control?
Yeah, so it absolutely can, because it doesn't require anything extra. So literally, it doesn't require any extra sensors. It doesn't require anything more than a normal, structure that you already have in a grid following inverter. So the only change essentially is that instead of having a PLL here and actually extracting your omega from a PLL. So this is just replaced by this structure. This is a very simple structure. If you look at the details of the paper, each of them can be either a PI controller, or in the case of this one, for example, two of them are PI, one of them is just a P controller. All of them are very, very easy to design and easy to implement. So absolutely. So and the thing is that it doesn't require any voltage control at the point of connection. It doesn't even require to know the voltage at the point of connection. So this is in the very first version of this, which is this one. We even didn't, we used the terminal voltage of the inverter itself to do all of these things, meaning that you even don't need the sensor there. Typically in a grid following inverter, you've got a sensor at the point of connection for your PLL. But in this approach, you can only connect it to a terminal, a three-phase terminal somewhere in the network without even knowing what is the voltage there. And this structure can start injecting real reactive power without any PLL, without any voltage control, without even any voltage sensor, relying only on its terminal voltage. But in some of the variations that we came up with, it can also look at the PCC, doesn't matter. You can also look at the voltage there. But long story short, yes, it can easily be retrofitted in the existing structures, and it can actually easily work in existing structures. We also had a very we actually tested all of these controllers against each other. I didn't put that paper. I should have put that paper, the reference to that paper, in the presentation. We compared these power synchronized structure with a normal grid following inverter, and we looked into a number of scenarios, testing the stability of the system, looking into the frequency, impedance-based analysis, and all sorts of analyses to show whether the system is performing better or the same as grid following inverters. And in every single scenario, it is either the same or performing better. When we are looking at impedance-based analysis particularly, it shows us that it actually remains pretty much stable. It's not impacted by grid impedance almost at all. So the impact of grid impedance on this structure is very, very little. While in a PLL-based system, well, we all know that the weaker the grid is, the more problems you will get in your grid following inverter. Yeah, so absolutely possible, and it probably can be even a better approach. Yes. Yet again, this is another thing that we are hoping that an OEM will approach us and we work with them and see whether this can be used in a product.
Sounds good. How will the adaptive control of D&J of VSG control affect the inertial support provided by VSG?
Not at all. So, you know, you can actually, it won't be actually changing much your initial support. You can actually, you know, have all of the performance that you require. You can set them prior to design, and then based on that, come up with your D&J to get the performance that you require. So it wouldn't change things much. Again, I very much recommend reading this paper and understanding all the derived equation, and it will tell you exactly the relationship between all of the parameters and the grid impedance and the system strengths. But the short answer is that it is up to you to define and design the performance that you require, and based on that, adaptively tune them. One thing I think I did mention it before, but you know, you don't have to adaptively tune it all the time. We've just put it there for just the sake of completeness of the paper. But you don't have to do it all the time, because most of the time this adaptive tuning is not required, because most of the time your grid is not changing that often. So this adaptive tuning either can be limited, or maybe like once every like month or so, or because like I said, it's very the changes in the grid are not too frequent. So it doesn't have to be always adaptively changing its D&J. It can actually, you can fix it, and then every now and then look at your grid, and if something has changed, then tune it accordingly. But you don't have to change it all the time.
So I'll jump over one question because the next one is related. How would adaptive tuning sit with existing requirements for fixed settings with rigorous setting change management process?
Oh, that's a very good question, I guess.
Yeah, that's a very good question.
Yeah,
Exactly.
that's a very good question, because these days, obviously, if you change something in your controller, often you have to go through all the connection studies that you've done, and you might repeat them. That's a very good question. I think then the answer to that is, okay, you just do the tuning once, and when you know that your grid is there, when you know where you're connecting to, you do this tuning in the beginning, and then you put your system there. Then you probably can only monitor the grid strengths and see if something has changed at that point of connection. And then maybe you want to decide that, okay, now it's the time to change our tuning to get better performance. And then maybe, well, but I totally get it. It is not easy to change, because every time you want to change it, you have to go through all sort of tests and connection processes again, unless operators come up with easy to implement ways of these tunings or changes in the controller. But I totally agree. When you connect an asset, changing the controller is not an easy task. Unless, well, I'm just thinking like on the fly. One thing that can be done, maybe prior to the connection, you can do a number of different, you know, settings, a number of connection, and sorry, a number of tuning, and say, okay, all of these tunings are good, all of these tunings pass the criteria. So maybe in the life of the project, if need be, and if we realize that the grid has changed now, and we would know that if we change it to this particular tuning, it can provide better performance, then you might be able to agree with, come up to an agreement with your operator that, hey, during the lifetime of the project, if the grid strength changes, I might want to tune again, or change the tuning to this one, because I know that this gives better performance. So that's one way. But again, I acknowledge that this is not easy to adaptively change the performance because of all the constraints. Again, maybe one option would be having a very fixed number of tunings ready for different types of grid strengths. and you might want to change. But yeah, totally, that's a challenge. That's a challenge.
All right, thank you, Behrooz. We'll wrap up now, but as I mentioned in the beginning, we'll address all the remaining questions offline. Behrooz, I hope it's okay with you to follow up.
Absolutely, absolutely, not a
right.
problem.
Thank you so much. I'll wrap up. I want to thank you, Behrooz, again for really informative presentation, and the audience for their attention, for staying over to listen to Q&A. As I mentioned earlier, an email will go out once the file has been posted, and we'll answer all the questions that we didn't get to as quickly as possible. The next GPST ESIG webinar on use of probabilistic resource adequacy methods will be held on April 26, and it will feature Aidan Tui, Genevieve Demijola, and Iman Linoy from EPRI. Further information on all of our webinars and meetings can be found on our website at www.esig.energy under events, and our newsletters and informational emails also contain that information. Behrooz, thank you once again for this very timely and informative webinar, and thank you all for your interest. We look forward to seeing you again in the near future, and in the meantime, everyone, take care, stay safe, and goodbye.
Thank you so much for having me. Have a good one.